In this video, one of a series I am making about the Collatz conjecture, the 3x plus 1 problem, I want to look at the question of odd and even sequences in more detail to explain more clearly the reason why odd sequences can be used in place of even sequences and why they are more easily understood. So in the graphic, in the two line charts, I illustrate that odd and even sequences actually look almost identical. The one thing that you might notice is that the scale on the even sequence is an order of magnitude greater than the scale on the odd sequence. So you can think of the odd sequence as the skeleton and the even sequence as a lot of flesh and fat that actually contribute nothing to the anatomy of the problem. So how do I arrive at the odd sequence? Well, I use a function that is a little bit intimidating because of the way I presented it here. This is actually sort of the purest form of the function. Without getting into the nitty-gritty of it, this actually explicates why Collatz sequences can be reduced to this form of pure addition and subtraction without need for multiplication. But I've explained that probably more clearly elsewhere in another video. What I want to do here is prove to you that the input and output generated by this function is a proper superset of the odd numbers of any Collatz sequence. So let's compare the conventional sequence with the odd-only sequence. So for sequence 43, for example, the odd-even sequence is this long series of numbers 43, 130, 65, 196, 98, 49, ending with the usual 5, 16, 8, 4, 2, 1. Now, it's obviously a jumble of odd and even numbers, but using the function I'm presenting here, you can actually completely eliminate the even numbers. So the odd-only sequence contains every odd element of the odd-even sequence. None of the even numbers, obviously, and it throws in a couple of additional odd numbers, which make it a proper subset of the odd-even sequence, but a much more economical one. So that's the main message I want to get across. Now, the function can be represented in a much more simple way, which is and note that here we are using the congruence representation, where we're saying n plus 1 is congruent with 0 mod 4 and n minus 1 is congruent with 0 mod 8. Well, another way of saying that, and a much more easily understood way of saying that, is if n plus 1 is divisible by 4, multiply by 1.5, subtract 1. If n minus 1 is divisible by 8, multiply by 0.75, add 1. And in all other cases, multiply n minus 1 by 0.25. Now, the consequence of this is an input-output table. And the inputs A, B, and C correspond with the three operations I've just described, and the outputs from each one correspond with the odd numbers in a Collatz sequence. So, for example, if we look at 43, the output is 65. If we look at a smaller number, because I don't want to go off the table, 37, the output is 9. And in both those cases, the multiplier is 1.5. Thank you.